Hi Math 107. In this video we're going to be looking at how to derive the annuity formula. Specifically we're going to be looking at the part of the annuity where we are making our regular payments into the account. So this is before we actually retired and started to do any sort of payout. The formula that we're working towards is going to be highlighted over on the right side of the screen in the red box. So we're going to take a longer way to figure out how did they get this formula instead of just taking it on faith that what they provided for us is correct. In order to do this, it might make it a little bit easier if we hold some of the variables fixed by giving it by assigning it a constant value. So in this case, what we're going to go ahead and do is we're going to assign a monthly, an annual, APR of 3%. We are going to assume that we are going to be compounding our account and our savings on a monthly basis, hence the reason why I have K is equal to 12. And we're going to go ahead and say that the deposit amount that we're going to contribute is going to be $500. And in this case, since we are compounding monthly, we are making a $500 payment every month as well. So what I would suggest doing is, before we get too far into the video, feel free to pause it and go ahead and grab either a notebook or some paper to follow along. All right, so to begin, what we're going to be doing is we're going to be kind of starting off with our compound interest formula. So to begin, we're going to start with P sub t is equal to P sub 0 times the quantity of 1 plus r over k raised to the k times t. So in order to kind of do a little bit more work with this, we're going to make some edits to it. So when we were looking at the compound formula, remember in that situation, we were just depositing one lump sum of money and then not touching it for however long. In this case, the amount in the account is going to change both because there is going to be interest that is going to be compounded every month, and you are also contributing something new every month. So we have to adjust this. So one of the first things that we're going to do is we're actually going to be technically looking at this problem 1 month at a time. So we don't really need to raise it to any sort of power because we're essentially resetting our analysis of the amount of money in there every month, because the previous deposit is going to get interest, and then we're also going to add in a new payment, which, since it just got into the account, doesn't earn any interest. So we're going to change that. And because of this, I'm going to change our subscript values here too. So in this case, I'm going to use m on the left and then m minus 1 on the right. So m minus 1 is going to assume prior month, and then m is going to represent current month, because again, we are looking at these things 1 month at a time. The other thing that is different is that we are making a deposit every month, and I think I probably said this at this point probably around 5 times, so I apologize, but hopefully it's sticking. So what we're going to do is we're going to add a plus d in order to indicate I'm paying a deposit at that time. All right, so let's go ahead and start by investigating a pattern, okay? So before we can really get into the nitty-gritty, we actually have to kind of see what's happening every month. So let's go ahead and start. I'm just going to move my screen up a little bit. And I'm going to try to do my best to color code this as well. So to begin, let's start off with P sub 0. So in other words, you've walked in, you have said, I'd like to start an annuity, and they're saying, great. You'll start next month. So at this point, we are just going to say that you have $0 in the account. You've just agreed to start one, but you aren't going to start making payments into it until the next month. So then the next month comes along, and we're going to say that's P sub 1. And here is where we're going to start using the formula that we've kind of edited up here. Okay, so if my P sub m is P sub 1, then my P sub m minus 1 must be the prior month. So we're going to do P sub 0, and that's going to be equal to 1 minus we said that our annual interest rate was 3%, and we were being, and that is being compounded monthly. And then we are going to add $500 to this. So in order to kind of streamline this a little bit later, I'm going to do a little bit of work here now. So in other words, I know that p sub 0 is equal to $0. So I'll put 0 in there, and I'm going to just clean up what we have inside of the parentheses. So, oops, and at this point, sorry, that should be a plus. So in case you caught that, good on you. So here we have 1 plus, and then 3% divided by 12 will give us 0.0025 plus 500. Now, I know in this case right away, 0 times this quantity is just going to 0 out. So my result then will be p sub 1, I'll just bring that down, is equal to $500. Okay, so we're just going to continue in this fashion. So the next one is going to be p sub 2. And again, p sub 2 is going to be equal to the prior month's balance. It's going to earn that interest. And actually, I'm going to go ahead and clean up this and just say that this is 1.0025 plus 500. So that new payment of 500. But I know that p sub 1 is equal to the 500 that we found in the previous one. So p sub 2 ends up being 500, so I'm just substituting that in, times 1.0025 plus 500. So far, so good. At this point, in order to see the patterns, I'm going to leave this alone. I'm not actually going to continue to simplify this down. And hopefully you'll see why in a little bit. So let's go to month 3. So month 3 will be the balance from the prior month, and that's going to get an interest charge. And then you are also contributing your new $500 payment. So again, I'm going to do a substitution here. So p sub 3 is going to be equal to that whole p sub 2. So I'm going to write this as 500 times 1.0025 plus 500. And remember, this replaces that entire variable for p sub 2. So then I still have that all being multiplied by 1.0025 plus 500. So I have a big quantity here, right? So I have this factor times this factor. So what I can do is distribute. So distribute to this first term, and then distribute to this second term. Remember that terms are separated by addition or subtraction signs. So if I clean this up, then my p sub 3 is now equal to 500 times 1.0025 squared plus 500 times 1.0025 plus 500. So if we kind of look at this, we technically have basically the 1.0025's exponent is decreasing by 1 within each term. So here it's squared. Here it's technically raised to the first power. And here you would technically write a 1.0025 to the 0 power, because anything raised to the 0 power is just 1. So when we simplify it, it simply looks like so. Okay, let's do one more. Scoot this up, because I think we can still see everything that we need to see. So now let's come to p sub 4. Again, p sub 4 is going to be the previous month's balance, and it's going to get its new interest charge. And then we are also going to add in our new $500 deposit. Of course, we can redo the substitution. P sub 3 is going to be equal to 500 times 1.0025 squared plus 500, oops, times 1.0025 plus 500. So it's this whole thing that's replacing piece of 3. That is being multiplied by the 1.0025, as is indicated here. Oops, and sorry again, I see what I did. That should not be there. That should just be 1.0025. I apologize for that. And then again, we have our $500 new deposit. So again, we can go ahead and distribute. So here we end up having 3 terms because they're being separated by addition signs. So we would be distributing the 1.0025 to each of these terms. This simplifies everything to become p sub 4 is equal to 500 times 1.0025 cubed plus 500 times 1.0025 squared plus 500 times 1.0025 plus 500. Again, we're seeing that decrease, that descending order of our exponents. So we could keep going like this if we really wanted to, but it's going to become very tedious. So I'm going to go ahead and try to generalize this. So the generalized form that I'm thinking of doing would be, well, we would have p sub m, and that would simply kind of become, well, 500 times our 1.0025, and since I'm saying m is equivalent to 4, then 3 is 1 less than that, so I would do m minus 1 to indicate it. Then the following term must be 500 times 1.0025, and again, if 4 is going to be represented by m, 2 is 2 units less than 4, so we would write that as m minus 2. We know that this is going to go in descending order, so I'm just going to use an ellipses because, again, since I'm working with variables, technically it would never end. So I'm just kind of saying, and at some point, I started to get back into regular numbers so that it's 500 times 1.0025, and we could technically raise that to the first power if we wanted to see it that way, plus 500 times a 1.0025 to the 0 power. But we really don't write it that way because we know that 1.0025 raised to the 0 power is just 1, so we don't really need to see that here. And also 1.0025 raised to the first, we really don't ever write an exponent of 1. We assume that it's there if we don't see it. If the exponent is anything other than 1, it should be written in there so we can visibly see it. Okay, so at this point, what we have here from calculus is called a geometric series. It's just a little bit of a bonus for you, or if you're interested, feel free to dig a little bit deeper, maybe search online. So there is a way of handling geometric series because we don't want to leave it in this format, because you could imagine that the formula technically changes depending on the time period or whatever point in our investment that we are looking at. We don't want this to kind of be open and recursive. We want this to be a closed formula. So we want to be able just to go to it, drop in our numbers no matter what point in time we are interested in, and then get our answer. We don't want to have to construct this, especially if it's going to generate a really long string like we're seeing here. Okay, so in order to deal with this, the geometric series suggests doing the following. So we'll do this in blue. What I'm going to do is I'm going to take p sub m, and I'm going to multiply it by 1.0025, so the value that we have as our base for our exponent. But what I do to one side, I have to do to the other. So I'm going to take that 1.0025, and I'm going to multiply it by everything that we have on the inside on the right-hand side of the equation. bear with me as I try to get all of this down, and I hope that this is 1, visible, and 2, neat. And by neat, I mean legible, although if you think it's neat as in cool, then that is also a bonus. All right. So basically at this point, you're probably thinking, great, you made it bigger, and therefore in some cases worse. So again, bear with me. We're going to clean this up a little bit. Again, we can distribute the value of 1.0025 that we have on the right-hand side. And this is where the trick is going to come in, or you will see it soon. So essentially, every term that we see on the right-hand side, even those included in the ellipses, are going to get multiplied by this factor of 1.0025. So this cleans it up to look like so. 1.0025 p sub m is equal to 500 times 1.0025 raised to, and here's where we want to kind of be careful here. So technically this 1.0025 is being raised to the power of 1. It is also going to be multiplied by 1.0025 raised to the power of m minus 1. Our exponential rules say that if the bases match, which they do, then we would add the exponents together. So m minus 1 plus that 1 would give us an exponent of m. Likewise, if we come to the second term, we have 500 times 1.0025, and again, we are doing an m minus 2, and we're going to add the 1 from the factor that we have on the outside. This becomes m minus 1. Oops, let me use a better color. So basically what we're doing is we're bumping every exponent that we had previously up by 1. So this keeps going. There's our ellipses. Then we have 500 times 1.0025 squared plus 500 times 1.0025. So as we can see, every term now has that 1.0025 attached to it. So this is not the end of the road. This is really us just fashioning a tool to help us create that closed form equation, or that closed form formula, excuse me. So now what I'm going to do is I'm going to basically line up the equation that I have in green and the equation that I have in blue. Okay, so let's go ahead and scoot this up so that I have a little bit more space. So I'm going to go ahead and rewrite what I have in blue. So I'm going to have 500 times 1.0025 raised to the m plus 500 times 1.0025, oops, and I see that I missed my 5 again, raised to the m minus 1, plus I'm going to put in my ellipses, and I'm just going to finish everything off with that 500 times 1.0025. So in case you're wondering, you're like, well, wait, what happened to the 500 times 1.0025 squared? I really just kind of moved it in here. It's still there, it's just hiding inside the ellipses. And you'll kind of understand why I didn't want to necessarily put it in here as we go through. Okay. So let's go ahead and put the green equation underneath it. So I have p sub m. As soon as my pen decides to cooperate with me. Let's try that again. P sub m is equal to, and my first term is that 500 times 1.0025 raised to the m minus 1. So what I'm going to go ahead and do is I'm going to deliberately put it underneath its matching term that I have in blue. Okay. Again, this term of 500 times 1.0025 raised to the m minus 2, I'm essentially just kicking it inside the ellipses. It's still there, I'm just not writing it out visibly. So I'm just going to drop my ellipses in here. My next term, 500 times 1.0025, and then my last term of plus 500. Now what I'm going to go ahead and do is I'm going to do a subtraction in order to get rid of all of those middle terms. So here's what that's going to look like. I'm essentially going to distribute a negative to each of these terms that you see here. And hopefully you can see them that I've highlighted them in red. So what we end up getting, first off, when we take a look at what we have on the left-hand side, we end up getting 0.0025 times p sub m. There's nothing here to subtract with the top term that I have, so that's just going to come down as 500 times 1.0025 raised to the m power. This cancels itself out because they are direct opposites. Everything in the ellipses as well, they are all matching terms with each other, one being positive in blue and one being negative in green. They all cancel each other out. So essentially we took a huge mess and we collapsed it just by using this trick. These terms as well, they match. One's positive, one's negative, so they will cancel each other out. And then I'm just left with that 500, that negative 500, that's kind of waiting on the tail end. So we're almost done with our work. At this point, we just want p sub m by itself. So what we're going to go ahead and do is we're just going to divide both sides by our 0.0025. And now we have p sub m is equal to 500 times 1.0025 to the m power minus 500 all over 0.0025. I'm going to do a little bit of a visual cleanup here. I notice that I have two terms here, because again they are being separated by the subtraction sign. Notice that both of them have a 500 in them. So what I'm going to go ahead and do is I'm just going to factor that 500 out, and what I have left in the first term is my 1.0025 raised to the m, and for the second term I just have a 1. And if you're not sure why, go ahead and redistribute that 500 back in. I should then get back to this formula. Okay, so we're essentially done here. I'm just going to go ahead and rewrite this ever so slightly differently. So to begin, I'm going to say this 500 here. Well, that we had represented with the lowercase d. If we go inside the brackets and then inside the parentheses, that 1.0025, if you go all the way back up to your work, that is the same thing as 1 plus r divided by k in our situation. Likewise, the 0.0025, that's going to be your r divided by k. That's how we obtained that value. We have our minus 1, and since it's a constant, we don't change that at all. Here are the last few kind of edits. The m here, this represents how many total times we are going to be compounding. So in this case, the m is going to be our k times our t. And again, our m is representing the final time cycle that we're interested in, and we are going to represent that by t. As you can see, we have gotten back, we've gotten back, there, now you can see everything, and I haven't slashed through anything. We've gotten back to our original formula, or sorry, our goal formula. Let me scroll all the way back. We've done a lot of work. There's our original formula. That's our goal right here. So, again, coming back here, again, by holding a few values fixed and going through the process, and then using a trick from calculus about geometric series, we've been able to recreate how that formula was derived. I hope that this has shed some light on the process, and as opposed to just reading through the book or just accepting the formula at face value. If you do have any questions, please let me know.